We move to the next keynote speaker. So it's Professor Guido De Croon. So Guido De Croon is a professor of bio-inspired micro-air vehicles in the Department of Control and Operations at the Micro-Air Vehicle Lab at Delft University of Technology. His research interests include the new bio-inspired approaches to AI, efficient control techniques, and improving the design of flapping wing drones. This involves developing computationally efficient algorithms for robot autonomy involving computer vision and evolutionary robotics. Very relevantly for our mission, he led the work at the Micro-Air Vehicle Lab that succeeded in making a swarm of 33-gram drones capable of exploring an unknown indoor space and returning to the departure point. So we are very much interested in your presentation. Thank you for coming. You can start.
Okay, thank you very much for the introduction. So I'm glad then that I took this topic as the talk. So because I'm indeed going to talk about the AI behind swarms of autonomous tiny drones. And I'm also going to give a bit look behind the scenes. So what I'm going to start with is a project that I started, I think 5 years ago now. The idea was to make swarms of tiny drones that would be able to help, for example, for search and rescue missions. So here we see a building. This is an apartment building. This is not the way that you want to find your apartment building when you come back home. Probably there has been some earthquake, and you see some human rescue workers on the building, which is quite hard to access. And what you would like is, for example, drones to help these rescue workers to quickly map out such an area, find survivors or other information that you might like, and then help the rescue workers to focus their efforts on the right places. Now, this was a project that I led from TU Delft, but it was together with Radboud Universiteit and University of Liverpool. And it may not be completely visible, but this is a photoshopped image. So this is not reality. And actually, we've been working over the years to try and make this a reality. So before we dive into the matter, perhaps some bigger questions like, okay, why would you want swarming in the first place? Well, there's some pretty evident reasons for it. So if you want to cover a certain area, for example, in search and rescue, if you have multiple drones or many drones, then they can cover such an area quicker. It's as simple as that. And if you have a swarm, then the solution is also scalable. So if your area is twice as big, then you just deploy twice as many drones and the system should be able to cope with that. And if you have a swarm, then you also have quite a robust solution. So if many tiny drones fly out and they map out the area, it may happen that one of them actually has a problem, gets stuck. Okay, this is not end of mission if you have a swarm. It's just basically calculated up front that such things will happen. So having a swarm makes for a robust solution. Now we focus on small drones within these swarms for many reasons. One is that small drones can be made extremely safe, so perhaps even inherently safe around humans, which is of course essential if you do search and rescue, because you don't want them to pose a danger to survivors, and you want them to be super safe. But also if you had a look at the building, they have to fly up, but they may have to pass also in very narrow spaces. And by definition, actually, indoor flight is quite narrow. So passing through a door, for example, if your drone gets bigger, that becomes a real challenge. If your drone is smaller, it's actually much easier. And they also have little aerodynamic impact on the environment. It basically means that, if you fly something, if it's heavier, it needs to push air down. And it pushes much more air down than a smaller vehicle that is much lighter. And this is not always super important, but for example, we also work on swarms of drones in greenhouses, and then the downwash, so the air that's pushed down by the drone, can actually damage the plants if the drone is too big. And so these are also important aspects. And finally, very importantly, when you make them very small, you can potentially make them very cheap and hence available in large numbers, which then is important again for the swarm. Now, so there's these advantages that are quite significant, but it also brings about huge challenges. So these drones have very little energy and a low payload capability. And little energy is of importance, of course, if you want to cover a certain area. Also, the smaller you make a drone, the faster its dynamics will be. So you need to actively regulate and control the drone on board. And this control has to be faster. And we just heard how important it is to have fast control on robots. Moreover, they will have little memory and little computational power. And they will have very few sensors in general. And moreover, if you have sensors on these small vehicles, typically they will be of low quality. And so these are important challenges. And to illustrate them a little bit, I will show you the drone that Julia was talking about. So this is the Crazy Fly drone. It's made by Bitgrace. It's a Swedish company, and we just bought them there. We bought them with 2 decks. So a multi-ranger deck. It has 4 small lasers to see distances to all the sides. So this is the multi-ranger deck here. It also has a flow deck that you cannot see. It's a little camera that looks down to see the velocity, together with a little laser ranger for the height. And this thing, it's in diameter 9 centimeters, so it's very small, and it weighs 33 grams in total. It has a small STM32F4 chip on board, which, let's say, together with the electronics, it weighs roughly 4 grams. It consumes 200 milliwatts, and it has 192 kilobytes of memory. So that's very little memory. And yeah, it's like less than most Word documents that you'll be making, even if you don't put that much text. Now, to compare that, so here's a diagram with other processors. Most people, when they do AI on drones, they use the NVIDIA TX2. It weighs 85 grams, has 8 gigabytes of memory, and it consumes 7.5 watts. And if people go really lightweight, then they use the Odroid C2, which weighs 40 grams, has 2 gigabytes of memory, and consumes 3 watts. But if you look at it, then the Odroid C2 is heavier than the complete Crazy Fly robot. So this is the challenge that we'll be trying to solve, and I will explain to you the kind of solutions that we use to do that. Now, I was seeing part of the presentation by Marco, which was very interesting. I saw some of these images, so actually he already introduced it for me, so that's very nice. And so the state-of-the-art method to autonomy is basically to make maps, to use simultaneous localization and mapping. And what we see here is a picture of a self-driving car, which has indeed a laser scanner on top, which scans 360 degrees around and can scan the environment in high detail. And the algorithms of SLAM then, they make a map of the environment that expands over time. This is the most successful approach. And sometimes people ask me, okay, why can't you use that? Well, we can't use this solution because on our drones, we cannot carry the sensors. So we definitely cannot carry a laser scanner, for example. We cannot power it either. We don't have the computational power to make these maps, to maintain these maps, to do loop closure within SLAM. We don't have that computational power, and we really don't even have the memory to store such a map. So we cannot, unfortunately, we cannot use this most successful and major approach to autonomous navigation in robotics. So that's quite a blow, and I feel that many of you are a bit sad, by this fact. And you may wonder, is there a solution? So is there a solution, Guido? Well, there actually is, and I think we all know vehicles that actually solve this. So if we look at small flying insects all over the world, they're very successful as a type of animal, actually. And this is a fruit fly. The fruit fly is as big as a grain of rice. So this is zoomed in, by the way. So luckily, but it's as big as a grain of rice, but it's able to fly, avoid obstacles, navigate, find food and shelter, interact socially with other fruit flies, learn. And it does all of this with only 100,000 neurons. It's tiny brain. It has a tiny brain, and it's able to do all of these things, which tells me that we actually have already enough computing power, probably, but we just should learn how to use it. So what should we do with it? Now let's illustrate the different kind of thinking that I think we should use if we want to make tiny robots autonomous and navigate in complex environments. So here we have a picture. So on the bottom we have a dragonfly, and on the right we have a fly. And the dragonfly wants to eat this fly, and the dragonfly is actually pretty smart. So I don't know if you can see my mouse, but so this dragonfly, it actually flies straight towards the point where the fly is going. And that's quite smart. So yeah, you may wonder, Guido, why is this smart? So I have 3 children, and my youngest one, if I play football with him, if I kick the ball straight to him, it's okay. But if I kick the ball a bit to his right, my kid will run towards where he sees the ball. So first he goes towards the ball, running towards it, and then the ball passes him on the left, on his left, and then he runs behind the ball. So he runs to where he sees the ball, and that's why he doesn't intercept it very well. Now you may say, okay, Guido, that's just in the Dutch genes. That's why you're not so good in football. But it actually stops when they grow up. They actually then start to run towards where the ball is going. And the dragonfly does that naturally. So it naturally flies to the right point. Now, if I ask engineers to make a solution for this problem, they come up with something like this. So a procedure in which the dragonfly first detects the fly, then determines the velocity of the fly, determines where it's moving to in space. So it's like a space-time trajectory, and then plans to get to the same point in the same time as the fly. And to be honest, so this plan sounds logical, but it's quite complex. It's a complex solution to a difficult problem, because detection is hard, velocity estimation is hard. It's probably noisy. Projecting into the future is hard, and this can take a lot of computational power. And so if you ask biologists what the dragonflies do, then you get this answer. Let's keep that small moving thing in the same place in my image. If the dragonfly keeps the fly in the same place in the image, then it will fly straight towards where the fly is going. And this very simple control rule is, of course, very simple to implement. It takes very little computational power, and it's actually very successful. And so this is the kind of solutions we need. We need simple behaviors to solve complex problems. Now, you may say to me, okay, Guido, there may be more complex tasks. One complex task, by the way, is finding odor sources. And so what we see here is strawberry, which personally I would not like to eat, but what you see here is a trajectory of a fruit fly. And this fruit fly is definitely interested by this rotting strawberry. And what they do is, so this is a very complex task, because in robotics, this is basically an unsolved task. And insects do it all the time, like the fruit fly. And what they actually do is, to solve more complex tasks, is to link together these simple behaviors. And for this task specifically, what the fruit fly does is, if it has wind from the side, it will first cast, so it will go orthogonal to the wind. And then if it senses the strawberry, if it smells it, it will go upwind. If it loses the smell, it will start casting again. And you see that here, it's casting, it smells it, goes upwind, it loses it again, it casts a bit, goes upwind, and then in the end, this brings it to the strawberry. And so we can tackle more complex tasks by linking these simple behaviors. Now, can we apply that to drones? Yes, we can. And so this is the Delphi Explorer. It weighs 20 grams, and we presented it actually at the end of 2013, and we published on it in 2014 at IPRA. It has a 4-gram stereo vision system. It happens to have actually the exact same chip that is on the Crazy Fly, as you already know it a little bit, so it's not that powerful. 168 megahertz, 192 kilobytes of memory. And what we did with this system, we were able to make an algorithm to do real-time stereo vision on it. That was already quite a challenge. And that took us most of our processing. But then we made a very simple behavior that was very successful in doing obstacle avoidance. Now, I first want to illustrate to you the challenge. Yes, so we have, and I hope you can see my mouse, we have a Delphi here. The special thing about the Delphi at the time was that it had a tail and it could not hover. So it would always have to fly forward with a certain speed. And so it needed to to make a circle. And so if it would start a circle too close to an obstacle, it would just hit it nonetheless, because yeah, it had a certain turn angle it could take. So what did we do? We had the Delphi, and it had this droplet shape, this inverse droplet shape. It wanted to keep this free of obstacles. So if something would enter into this droplet, like a wall here, it would start a procedure to still fly straight and then circle in front of the obstacle to look for a new direction. Now, why wouldn't we turn immediately? And that's also a reason why the shape of the droplet has this triangle. On the drone, we had these cameras that basically are from old mobile phones, and they have a very small field of view, so only 60 degrees. And while if you look at insects, they have very wide field of view vision, and we didn't have that. So if we would turn immediately to the right, we could bump into something here that we're just not seeing. So that's why we chose to fly straight, make a circle, choose a new direction. And here you see this represented visually, this behavior. So we have these simple behaviors, most of which actually are flying straight. So straight, straight, turn right, straight. And then we have these transitions between these behaviors. Like the fruit fly is transitioning between casting and surging. And we see, for example, that if something comes into this region here, we start still to fly straight, but we put a timer. And if the timer is above a certain time, we're at this point here, then we will start turning to the right. And there's these transitions. And in the end, we were able to ensure obstacle avoidance with this. So theoretically, if the sensor is perfect, we can ensure it will never collide. And actually, in practice, it also worked really well. So here is a test in our natural habitat. So our natural habitat is the lecture room. And when the students are not there, we can fly there. And so it keeps the drone, we speeded up the video, by the way, because it turns out that if obstacle avoidance is working, it's actually less fun to watch. But you see it flying around. It keeps its height with a pressure meter, and it uses the stereo vision to see obstacles and to avoid them with the algorithm I just explained. And actually, this worked very well in many environments, because we actually demonstrated this system in many different places. Yeah, and it basically almost always worked. And there may be some cases where basically our stereo vision was not good enough. And here you see these small images on board, and this is the stereo output. Now, in the beginning of my presentation, you saw these little quadrotors. So we made the step to these little quadrotors. So we mounted our stereo vision system on them. We found out that for quadrotors, dynamically, they're more difficult actually than the Delphi. So the old Delphi is actually passively stable in terms of velocity, let's say. So it will not drift to the left or the right, but quadrotors will drift. And that's why instead of only doing stereo vision, which we show here on the right, had two images taken by the left and right camera at the same time step, we also had to determine optical flow, which gives us information about the velocity of the drone. And so now we had to do both of these processes on our little chip in real time. So we also succeeded that, and we're pretty happy with that. But until now I've been talking to you about the intelligence of single drones, and I guess you are also interested in the swarming. So how can we put this now in action into swarms? And so many people perhaps think like, swarms, they already exist, right? So for example, this is a picture taken during the opening of the Olympic Winter Games in South Korea. It's very nice by Intel, with all these dots here, these lights are drones. And here they form the Olympic rings, but they also were forming a snowboarder, and it was really beautiful. And so these are many, many drones. It's a very difficult technological challenge, this as well, by the way. I don't want to downplay that, but I wouldn't call it a swarm because the drones are unaware of each other. And so they're following a predetermined GPS trajectory. If they deviate from it, they will just collide with each other. And so that's not very nice. And if you look in the literature on swarming, like the research on swarming, it always begins with these models from nature, like the birds that look at their neighbors and then they go away if they're too close, or if they're too far from the swarm, they go towards the swarm. But what we actually noticed when we started was that there was actually no way for small drones to see where the other ones are. And so where are the other drones was a question that I started on, I think is 5 to 7 years ago. And basically that was our biggest challenge. So to let them be aware of the other drones and know where the other ones are. So let's go over the options, because there was already some work in Switzerland in the EPFL where they were using infrared. And the challenge with drones is that other drones can be all around each other, right? It's they're in 3D, so yeah, you have a bigger problem than with ground robots. And with infrared, it meant that you needed many infrared sensors. And so this led to a bulky and power-hungry solution. Another thing that people work on is vision. So using vision to see the other drones. And also birds do this, definitely. But on our small drones, this was challenging because, like I just said to you, we have this limited field of view. In order to process the images on board, we needed to make them pretty small. And the drones are small. So basically, it's almost impossible to see them even as a human in the images. And if you think about it, yeah, the vision processing is always quite computationally quite heavy. So at the moment, and especially a few years ago, we were really not ready to do this on board. Then audio, I think also birds hear each other. And actually the EPFL also worked on audio, which I think is very promising. And you can hear perhaps the other drones. And by hearing, you can localize them. The only problem is that the drones themselves make quite a lot of noise. And because the drones are typically the same type, they make the same noise. So it's actually very hard problem. Now, there's a group in Hungary that had a very nice solution. So they have a very nice swarm outdoors. Each drone receives GPS, but it doesn't follow a predetermined trajectory. What they do is they communicate their coordinates to each other. And by doing so, of course, they can determine the relative coordinates to each other. And so it's very nice. It allows for swarming, but GPS is not always available. And especially indoors, it's just not available. And if you want to do a similar scheme indoors, you would need a big map of the environment again. So a common frame, a common map in the environment, which is impossible to get with our tiny drones. So there's one thing left, and that's the way that we try to follow, is signal strength. So if at home you have your Wi-Fi router, and you walk towards the router, you get more stripes on your phone. And this is the signal strength that is, the signal is getting stronger. And you can use this, of course, as well. And we use this. The nice points are there's no extra hardware required because you typically already have such a communication chip on board. It's low power, it's omnidirectional, and it's computationally very cheap. And there's two extra points, a little bit detail. And so here, interference is an issue. If we keep adding drones, then at some point we get problems because we get interference between the messages. And towards the future, I think vision and audio is super promising because it scales so well. But, we're not there yet, like I said. Now, what is our approach? And so we started this very early, actually. So in 2015, we were working on this. And this is an article that we published in the archive in 2016, and it's now published in Autonomous Robots. But here you have two drones. And like I said, they have this signal strength. And if you have the strength, then you can determine a distance. But you don't know if this drone is here or if it's anywhere else on this circle. And so how to solve that? Well, our solution was to have them communicate states to each other. And in this first study, we had them exchange their body velocity and their heading with the magnetometer. And so by exchanging this, the drones can filter information over time, and they can actually get pretty accurate estimates of where the other ones are. So this is illustrated with AR drones, parrot AR drones. They were constrained to fly in a 4x4 area. And normally, if without the avoidance, they would really hit each other within the blink of an eye. But with this solution, they were able for quite a long time not to touch each other. And we were using Bluetooth at the time, which we were also able to fit on these tiny pocket drones. So I hope that this renders a little bit over the internet, that you can see the video. But they're pretty tiny, actually. And also here, we're just using the Bluetooth that they had already on board. Now, if you want to go more accurate, then you should use ultra-wideband. And that's what we did in a later study. So this one. So we have a leader drone here. that has a coordinate. So it has a pre-programmed flight path, like almost figure 8. And these drones have ultra-wideband. Only the drones have ultra-wideband on them. And then they do this scheme, and they the followers, they try to follow the path of the leader. And as you can see, we're now accelerating it as well. As you can see, this works really pretty well. And we get really quite good results with like 10, 20 centimeters resolution of where the other ones are. And so, and this is, this can be used not only for avoidance, but really also for coordination between these drones. Now we put this together, these two things, so the obstacle avoidance with the simple algorithms, the sensing of the other drones with this communication means, and we made this drone. So it looks a bit strange. So it has the stereo vision system, it has Bluetooth for avoiding each other, and it has this flex PCB with little lasers, let's say, to detect also obstacles behind and to the sides. And then we flew this in one of our office spaces, this one, and here's the video of one of our flights. So Kimberly McGuire is the PhD student that was working on the project. She's starting one of the pocket drones here, one of the tiny drones, and then she starts the other one. And they're already sensing each other, but this one is not yet moving. And here she makes that one take off. And you see that they fly around, avoid obstacles, avoid each other. And we were quite happy. Although, it was not super stable and robust. And the main reason for that was that, we were basically putting together all these elements ourselves in a research project. And you get extra stability if you can, if you work towards a product, let's say. And so that's why we changed to another drone later. Now, I saw an elephant in the room in the previous presentation. There's also an elephant in the room here. We're very happy with it and with this performance, but if you want to use these drones for like search and rescue, they need to fly out, avoid obstacles, avoid each other. It's nice, but they also need to be able to come back, and navigation is a very big problem for this bio-inspired approach. And because with SLAM, with the map approach, up front, if you have a map, you can plan to come back in the map, right? So that's a clear solution. For bio-inspired research. And we know that insects can do it, but we don't know yet enough to implement exactly what they do. And so this is still an active research topic, and we had to tackle navigation. So we did, and we had a look at bug algorithms. And bug algorithms, they are typically, they're actually originally maze-solving algorithms. So to be honest, they're called bug algorithms, but they're not so bio-inspired in a sense, in my eyes at least. But the cool thing is that bug algorithms use no map and typically use no memory. So what do? So we have an agent here with a start location that has a target location. And wherever it is, it always knows the direction to this target. So it tries to travel to the target, but when it encounters an obstacle, it's going to follow that obstacle around. And they call this wall following. And there's also always a mechanism to transition again to flying towards the target. Like here, it doesn't see an obstacle anymore, so it goes towards the target, but it sees an obstacle again, and it starts following it. And by following these simple behaviors put together, it can reach the target. So that's nice about bug algorithms. The only thing is that in almost all of the bug algorithm studies, they're maze-solving algorithms, but they assume that the agent knows its location and knows the location of the target in a global map. And so, if you have this assumption, basically you introduce maps through the back door. And this is problematic, like I said, because we don't have these maps. And so we needed to solve this. So first we wanted to look at, okay, if you have these algorithms and you take away the assumption that they know their location perfectly, what happens then? And so instead of having a location, we said, okay, they know the start location, they know where the target is, but then they're going to track their own location by means of path integration, so odometry. And so they check, they know, okay, I have this velocity, so they integrate it, and then they use that as a position. Now, and that's this diagram here. On the vertical axis, we have the successful reaching of the target, the percentage. And on the x-axis, we have different algorithms. and we have different colors. So light blue means the path integration is perfect. This actually corresponds to having a map. And like this ALK2 algorithm, it then succeeds in 95% of the cases within a limited time. But if the odometry becomes a bit noisy already, it drops. And with a quite realistic noise, it really drops very low to 30%. And so these bug algorithms basically fail if you take the map out. And so how can we still...
Multiple robots fly.
Okay, I should introduce the next slide before. There's a virtual version of me that's going to tell you how our algorithm works.
Multiple robots fly off in different directions. Instead of mapping the environment, they deal with obstacles on the fly. When their batteries are at 60%, the robots fly back to a radio beacon at the ground station, again avoiding obstacles and each other.
So, to summarize, we have a swarm. In order to get coverage, we all send them into different directions. So they just have a desired direction. They start traveling there as if there's a target at infinity. And they start traveling. And then when they notice that their battery is at 60%, they do something else. Then we have one beacon at the ground station, which we think is a reasonable assumption. Because if you're a rescue worker and you send your drones out, you want them to come back to you. And carrying a small beacon with you is really not a big problem in this case. And what they do to go back to the beacon is they perform a gradient search. Because, like I said, if you go to your Wi-Fi router, the signal gets stronger. And so it's a bit like only looking at your mobile phone with the stripes and trying to find the router. That's what these drones are doing. And when they encounter an obstacle, they just will try flying around it. And so this made it all of a sudden possible to do such a complex mission with these drones. And the name of the algorithm, the swarm, means that we have multiple robots so that they can spread out of the environment. And the gradient part comes from following the gradient of the radio signal strength intensity at the home beacon. Now, I show you also this high-level view of a finite state machine in which we have different behaviors like move forward, follow wall, move away. This is mostly to avoid other drones. We avoid other drones again with radio signals where we have the lower priority drone moving out of the way. And then we have following this desired direction. And we have all kinds of transitions, between these states in order to get to a successful behavior. And so this really runs like super real time. I mean, this is like even on this tiny drone, we use very little of its processing actually. And I'm going to show you now that this is the drone again. I'll show you our real world tests. And so we have here high rise. Our faculty is a high building, and this is one of the floors. And the drones start at the beacon in the middle of the hallway. We put circles around the drones because basically they're so small, I'm not sure you see them over the internet like this. I hope you see the circles. And you see them flying around, they fly away in their desired directions. You also see them entering into these rooms. So here we have number 5. You see also a top view of what the drones are doing. And this top view we have reconstructed after the experiment. And so the drones are not aware of any map or top view or whatever. They're just following these rules that we set out for them. We have drone 1 that already went back. And we see some of the other drones also, like this blue one, 5 is coming back, 6 is coming back. This is interesting. 6 senses 2, avoids it, thinks it's gone, but then sees it close again, so goes away, so they avoid each other. And these drones come back, and we see that they basically visit all the rooms. And at this point, we have only 1 active drone left. It's in this room. It could go out, but I don't know, for whatever reason, it decides to make a second round there. So it makes a second round, and I can tell you it actually comes out and makes it till the end. I'll show you. So it comes out, there we have it, and then it flies back to the home beacon. You can see like they have limited flight time, but in this short time, and this is not their full flight time by the way, in this short time they covered this whole floor. And so here we have this map again where they went, and you see that they cover all of the rooms except for 1. And some of them cover the same room twice, and we'll come back to that later as well. But they do this very successfully. Now, we did this for 6 drones many times, for 4 and for 2. And what we see is that, yeah, of course, if you add drones, and then your coverage increases. The coverage per agent goes down a bit. And what we see is that, yeah, more drones means more coverage. But there is a law of diminishing returns. That's like when you move to another place and you ask friends to help you. If you ask 5 friends, it's still very beneficial. But if you invite 30 people to help you move, then it's no longer very useful. And the drones will be just avoiding each other, basically. Now, we also did a proof of concept in which we the drones with cameras. And so we put the camera on it. The camera is not used for navigation or whatever. It's just used for making images and storing it on an SD card. And the concept is that if they come back to the rescue worker, then the rescue worker can download the videos and look at them, or there can be some software that makes a map, you know, on a bigger computer. And what we see here now is drone number 1. It flies into a room with one of the victims. In the meantime, another drone detects another victim. But this drone number 1 is in the room with one of the victims, but it's the only one that had the lost video footage. So that's a pity. But look here at one of these other drones. Here, the yellow one sees that dummy. So it sees the victim that was missed by the blue drone. So you see why redundancy is actually useful in this swarm. If something goes wrong and they do cover the same space, either by looking there or flying there, it's actually useful. So a bit of redundancy is actually not so bad. Okay, that brings me almost to the end of my talk. I hope I'm more or less on time. So what's next? More complex environments. Yeah, I think we need to work, you know, these are real world tests. We did many of them. So I think for robotics, it's pretty good work. But, you know, if you want to go towards a product, you have a lot to improve. And also even in research, I think. Higher robustness of almost all the individual low-level elements. Higher precision of the inter-drone localization and navigation in full 3D. We also working on applications in the real world. So in greenhouses, I'm actually actively working with companies to have swarms of drones there to monitor the crop. In warehouses, they can keep track of the stock, for example. In a search and rescue, we're actually working now on drones that can deal with smoky or even, smoky is very bad, but smoky environments, but even dark environments. And how can drones still do there? The takeaway message of today for me is 3 principles of insect intelligence that we can use on drones. As simple behaviors can solve complex tasks. More complex tasks can be achieved by combining simple behaviors in an elegant way. And even more complex tasks can be achieved by means of swarming. This is the research team that worked on it. I especially want to mention Kimberly because she worked 4 years on it. And there were many preparatory studies with other people. I'd like to ask questions. And yeah, there's some killed darlings that I don't talk about. Very fast flapping wings, drone racing. We won a big drone race a few years ago. And we're working also on neuromorphic sensing and computing. So should you have questions about these things or you want to see the videos, then I'm more than willing to show them to you. So thank you for your attention. I'll gladly answer questions.
Thank you so much, Guido. Very, very interesting presentation. Okay, so we have the first questions. So which sensor or Bitcraze deck are you using for the swarm demo you show?
Yeah, so we really wanted to use, because yeah, we make quite some hardware ourselves. I mean, we're not great at that, but we can make some small electronics. But we didn't want to do that for this study. And we really wanted to work with what you can buy at Bitcraze. So we used the laser ranger deck, yeah, the multi-ranger deck, they call it. And we used the flow deck on the bottom. So there's a tiny camera that sees the optical flow. And then, of course, to provide scale, they use a tiny laser. And so we use these 2 decks. And typically it already has the what they call crazy fly radio, which is a radio connection that you have anyway, because you need to upload things or tell it to land if you want, or be able to communicate with it. And we used this thing for both the avoidance between drones and coming back to the base station. And this was really quite tough because it's a bit like Bluetooth. It's like super noisy. And so you can easily even improve on our results if you use, for example, ultra wideband on the drones. Yeah.
Okay, thank you so much. Other questions? Yeah, I remember some time ago you presented a relative localization method based on signal strengths and I think filtering that suffered from a problem. It required drones to move with each other. Did you solve this problem?
Yeah, so very good question. Thank you, Eliseo. So it's actually a few slides that I hit for the reasons of time, but indeed, so if you look at this problem of the filtering, then there's actually some situations in which you cannot find out where the other one is. So if they're both static, for example, then you know, yeah, this one is around a circle around me, but you will never find out because the distance always stays the same and the velocity is 0. And so there's these unobservability conditions. Now, we recently did a work with Shushuai Li, it's one of my PhD students, in which we did a few things. You know, this is a relevant problem because if you do formation flight, you typically want them to be, for example, fly parallel or even hover, you know, so these conditions actually happen during real flight. And we actually made theoretical analysis and also simulation that actually shows that if you get to such a situation, you will also get out of it again. And because this unobservability will lead to some action, which then makes it observable again. And so in practice, actually, this is much less of a problem than I expected at the time that I was presenting previously to you. So actually, this was an evident theoretical problem that in practice turns out to be much less. And we now also gave that then a theoretical basis. You have to do something as a scientist. So it's not so much of a problem, Eliseo.
Yeah, and is it dependent on the density? There is the second question. I think it depends.
Density. I don't know what he means with that. So the only thing is what we didn't solve yet is if you go to many drones. And so what we still have at the moment is that if we add drones, so if you have 2 drones, you can communicate very fast. This one says, hey, this is my velocity, and then that one says my velocity. But if you have then 3 drones, then they already have to divide the time in 3, let's say, because they shouldn't talk in the same time, because then you get interference. And so you can imagine that if you keep adding drones, that basically it goes slower and slower. And at some point, it becomes too slow to be practically useful. And so this is something we didn't solve yet, but I must say we also, we had working setups with 7 drones, which is nice. But I would like to go higher, of course. So I don't know where the actual limit lies with this technology. I do think that if you want to go to swarms of like 100, you need to solve this. So this is something we didn't solve yet.
Okay, thank you so much, Guido. Very, very interesting presentation.